Here we are going to discuss about the shape function of 1D bar element, and you'll observe people used to get confused about the shape functions derived in physical coordinate systems, shape function derived in natural coordinate systems, and the relation between these two coordinate systems. So here we are going to discuss all these things. Before jumping to here, let us discuss about the shape function and its properties. Shape function is nothing but a displacement function or interpolation function which we use to interpolate the value within the element. So here n1, here u is the displacement at any point, which can be written as the sum of the ni ui. Okay, so basically sum of the multiplication of shape function and displacement values. Okay, u is equal to n1 u1 plus n2 u2 plus n3 u3, like that. So shape function is a displacement function or interpolation function, you can say, which we use to interpolate the value at any point with the help of the nodal values. Here u1, u2, u3 are the nodal values, and n1, n2, n3 are the shape functions. Okay, so shape functions is the displacement function which we use to interpolate the values within the element. Now, if we see about the properties of the shape function, we will observe that value of shape function will be 1 at particular node, and at the same time value of shape function will be 0 at other node. Next property is that sum of the shape function will be 1. Okay, for example, if you have two shape function n1 and n2, then sum of the shape function will be 1. This is the major properties of the shape function we use in FEM. Now we will see how we can derive the shape function for a 1D bar element. Here, first we'll discuss the shape function in our physical coordinate system, which basically nothing but our Cartesian coordinate system. Here, you just see we have one element, okay, and this is the node 1 and this is the node 2. Here we have written x1 and x2 from this origin. Then the shape function can be written for this node 1, like this: x2 minus x divided by x2 minus x1. Now here x2 minus x1 is nothing but the length of the element. So shape function at node 1 will be x2 minus x by L. And for node 2 is basically x minus x1 by L. Okay, so this is the shape function when we consider the origin here. And we are assuming the shape function which is at a distance of x from the origin. Okay, now if we consider the element at the origin, okay, for example, if you consider element like this, where this value is 0 and this value is L, okay, then we can basically rewrite this shape function in this way. So x2 minus x by L, x2 is nothing but the length of the element, x is x by L. So basically shape function at node 1 will be 1 minus x by L, and at node 2 shape function will be x by L. Okay, so this two way we can write the shape function when we try to write the shape function in our physical coordinate system, which is our Cartesian coordinate system. Now we'll try to see properties of the shape function. So the property of the shape function is nothing but n1 will be 1 at node 1. So here what we're going to do, we have n1 nothing but 2 minus x, that will be your x1 by L. So here you can write x2 minus x1 by L, that is your L by L, that is equal to 1. At the same time, n2 will be x1 minus x1 by L, that is equal to 0. So here you just see the value of the shape function will be 1 at node 1 and it will be 0 at other node. Similarly, we also can do it for n2. Next, another important property is the sum of the shape function will be 1. So here what we can do, we can write n1 plus n2 is equal to 1. So what we can do, we just write L here x2 minus x plus x minus x1 is equal to nothing but L by L is equal to 1. Okay, so here we can see this is the property, second property of the shape function, that is the sum of the shape function is equal to 1. Now one may ask question, why the sum of the shape function would be the 1? So this question may arise to your mind that why it should be 1. Now see what we have learned, that u, which is displacement at any point, is nothing but your n1 u1, n2 u2, n3 u3, like that. Okay. Now if sum of the shape function is to be 1, then we'll observe it will ensure that the structure is showing the rigid body motion, or element has the capability to show the rigid body motion. Rigid body motion in the sense all the nodes are having same amount of displacement. There is no relative displacement. All the nodes will have same displacement, and there is no strain. There is no stress also. Okay, so the element should have the capability to represent the rigid body motion. That is one of the major important parameter of FEM. That elements should have the property to represent the rigid body motion in certain circumstances. Okay, now here you just consider one simple example where we have the rigid body motion. That means u1 equal to u2 equal to u3. That may be a constant value c. Okay, now here u we can write as your n1 c plus n2 c, n3 c, like that. So u we can write c times n1 plus n2 plus n3 plus like that is equal to u is equal to c. So here you just see, if the sum of the shape function is equal to 1, then we can make sure that element has the capability to represent the rigid body motion whenever required or whenever applicable. Okay, so for the same reason, basically we assume the sum of the shape function is equal to 1. If it is not 1, then what will happen? Our interpolation function will not be accurate. We may not accurately interpolate the value. We may not be able to accurately interpret the displacement values or strain values. Okay, so here this is the reason why the sum of the shape function should be 1. Here we have learned that how to write the shape function of a 1D bar element in our natural coordinate system. Sorry, in our physical coordinate system, basically in our XY coordinate system, which is nothing but our Cartesian coordinate system. Now, what we can do, we can also derive the shape function of this 1D bar element in our natural coordinate system. Natural coordinate system. Okay. If you consider the natural coordinate system, in that case, our shape function will look like this. Here, n1 is equal to 1 minus xi by 2, and here n2 will be 1 minus, say 1 plus xi by 2. Here, natural coordinate system is nothing but a coordinate system in which the maximum dimension varies in between 1 to minus 1 to 1. The dimension of the element varies from minus 1 to 1. Now, one may ask question, then what is the need to write the shape function in our natural coordinate system? Because already you have developed the shape function in our physical coordinate system. So what is the need? The answer of this is that if you have a irregular shape geometry, in that case, we may not have good result if we consider physical coordinate system. Okay. In such cases, what we have to do? We have to regularize the element with this assumption is that the dimension of this element will be in between minus 1 to 1. So here you can see that we are regularizing the shape of the element by considering the shape function in our natural coordinate system. And in this way, you also will observe later on that it is very easy to remember the shape function. It is very easy to derive the shape function, and also very easy to get the stiffness matrix through some mathematical manipulations. Okay, so this is the reason why we use our natural coordinate system to derive the shape function. So our shape function for linear element for 1D bar element will be 1 minus xi by 2 and 1 plus xi by 2. Here also again you just do the summation of it. N1 u1 plus n2 u2 is to be your nothing but your u. U is basically the population at any point that is equal to n1 u1 plus n2 u2. Okay. And here you can see, if we see that n1 will be 1 when xi when we measure at node 1. N1 will be 1 when we measure at node 1. So here you can see at node 1 the value of xi is equal to minus 1, and node 2 value of xi is equal to plus 1. So here you just write minus 1 and minus 1 plus 1 by 2 is equal to 1. So the value of the shape function will be 1 at node 1, and at the same time value of the shape function will be 0 at node 2. Okay, now if you consider value of the shape function at node 2, then node 2 value of the shape function at node 2, then value of the xi at node 2 is equal to 1, that will be 1. At the same time value of n1 will be 0. Okay, so value of the shape function will be 0 at node 1. So here you can see this way basically we can get the shape function in our natural coordinate system as well as your physical coordinate system. One more thing you try to observe that variation between these two nodes is linear. Variation between these two nodes is linear. So value here is u1 and here it is u2. The variation between these two nodes is linear. So what we can do, so basically it represents, this is our linear element. So from here you can see that when x is changing within the element 0 to L, or n also changing linearly. Okay, so here you can represent n1 like this, at n1 is equal to 1 at this point, and it will be 0 at this point. So this is the linear variation of the shape function. Similarly, this also will be 1, n2 will be 1 at node 2, and it will be 0 at node 1. So variation between these two nodes is linear. And for the same reason, the element will derive will be called as your linear element. Okay. Thank you.